And welcome back. Now, as you can see, we've got a flashing LED party strobe here, and we're going to talk about how we managed to get this working with the Arduino and pulse width modulation. But the original video was just far too long, so we're going to deal with this in two parts now. So the first part is going to deal with a very simple pulse width modulation type experiment, and then we're going to go on to actually describe how we get this thing working in the circuitry that you see in front of you right now on the workbench. Okay, now it's pretty interesting stuff and does deal with a lot about pulse width modulation, so bear with me. Let's get right on to part one. And welcome back, and today it's party time. Well, at the time of recording this, it's coming up to Christmas, so what better way to party along in your own home or small village hall or something with a home-built strobe. Now, as you can see on the workbench here in front of us, this here is in fact a commercial unit, a strobe. It's only a small little one because, well, if it fills a village hall or something, it's probably about as much as you might need. And in my former days, probably unknown to you at this time, I used to be a DJ. Yep, that's it. 40th anniversaries, 21st, 18th, I don't know, you name it, I did it. And this little thing was one of my first bits of equipment that soon got replaced after a while with a slightly bigger one, actually, I must admit. But to begin with, this was quite good. Now, I've had a look at the spec of this particular strobe, and all it says on there, look, is 0 to 10 flashes a second, and that's it. Doesn't tell you about the power or anything. But I have investigated, and basically the little xenon bulb thing in there is probably about 5 watts or thereabouts. But of course, it does discharge very, very quickly. Now, the thing you can see flashing on my desk, or rather interestingly, you can't really see it that well. All you see is a sort of a blue flash here, but you can't see the actual individual LED flashing. It's quite a bizarre effect I'm getting from the video camera here. Basically, the flash is so quick on here that the video camera doesn't really pick it up too well. And I'm thinking it's just picking up the sort of surrounding reflection. But never mind, take my word for it, it is the actual LEDs on here are flashing. So this is how we're going to make our little party strobe, and it works better than I thought it might do. Certainly that 4 watt, and that's a 4 watt LED there, runs off 12 volts, unlike this thing that used to run on mains. So it's all quite safe, really. Now, of course, a strobe like this has to work with a certain frequency. Obviously, it's pulsing every so often, isn't it? And what better way to do it with an Arduino, or a Nano in this case. Here we have a Nano attached to a little development board, and we use pulse width modulation. Now, I'm going to pretend that you don't even know what pulse width modulation is, or PWM, so I'm going to give you a quick 60-second sort of primer. So if you do know about it, take a deep breath, it'll soon be over. I know, yeah, well, I'm catering to all bases here, aren't I? So let's talk about pulse width modulation and how very, very easy it is using Arduino. And then, of course, how much easier it is these days by using a library. I know, I'm actually going to use a library this time so that we can adjust this pulse rate to something we can use. And of course, those of you that do know all about pulse width modulation and the Arduino, and are just interested perhaps in making a strobe effect, party strobe like this, are probably wondering how I've got this flash so low already, because the Arduino will not do that by default. And there's no trickery here. There's no 555 timer or anything like that going on. Okay, quick crash course in what's pulse width, can't even say it, look. PWM, pulse width modulation. What is it? And why is it so important to us in the Arduino world, not for xenon flashes like this, but generally in other things? Right, here's a quick overview. Now, for those of you who've watched my videos from the early days, in videos 14 and 15, I did a couple of videos there on pulse width modulation and how we can use it to fade an LED and adjust the speed of motors, and that's the primary use of PWM. It's basically to turn a motor on and off in such a way as to adjust the speed. So if you don't know what pulse width modulation is, let's think about this. If you have a motor, a nice little motor on your wheel of a car, say, right, so there's your motor spindle, Now, say that was a 12 volt motor nominally. You might think, if you didn't know about pulse width modulation, that to make this motor go faster or slower, you simply change the voltage of this motor. Now, so if you think, well, 12 volt equals full speed, and I don't know, let's just take a trivial, say 3 volt equals really, really slow, and anything like that would stop, say. Now you might think, well, if I alter the voltage between these two, I'm going to get a speed difference on here. And if the motor was doing nothing, that is just sitting on your workbench, that's exactly what would happen. There's no load on it. But what happens is, as you bring the voltage down, so the volts goes down, but then so does the torque. Now torque is the turning power. Okay, now there's quite a lot on Wikipedia about what torque actually means, but for us in the radio controlled model type world and things like that, it's the twisting power of this spindle. All right. Now at 12 volt, you might not even be able to stop this motor with your fingers, or it'd be very, very difficult if it's geared internally. Perhaps you might not even be able to turn it. Certainly, it'd be very, very strong and could whiz a car along. Say, if you had two of these, one on each wheel, for example, at the back of a car, you might find that you just wouldn't be able to stop it with your hand. But as you brought down the voltage, you'd find very, very quickly, once you got down to about 9 volts, the car wouldn't even move because it hasn't got enough power anymore. Because it's a 12 volt motor, you're trying to drive it at 9 volts, and basically it just doesn't want to know because the torque has now dropped dramatically. So what we need is a method of keeping the torque up at this sort of level, whereas the speed is going to be down at this sort of a level somewhere in here. And the way we do that is by delivering pulses of 12 volts to that motor. And by pulses, I don't mean pulses that you could do with your finger on a switch. We're talking many hundreds of pulses, hundreds or even thousands of pulses per second. Okay, so what this does, this delivers a 12 volt pulse to that motor many hundreds or thousands of times a second. That gives us the full twisting power of that motor, even though we're only doing it for a fraction of a second. And this is what then changes our speed by making these pulses thinner, if you like. So a little tiny pulse and a big gap, and another thin tiny pulse and a big gap. Or we can have a fatter pulse, a smaller gap, then another pulse and a smaller gap. Now this is the width modulation, and that's what we call pulse width modulation, because we're delivering pulses and we're changing the width of that pulse, the on period, and well, the maximum you can go to is basically delivering a pulse that's permanently on, or delivering a pulse that's permanently off. Makes sense, doesn't it, really? And the Arduino let you do that. In fact, the Arduino, between these two levels, extremes really, there's 255 different levels. We can have one pulse to 254 spaces, or we can have one pulse and for 254 pulses and one little tiny space, which will give us a huge boost, right? So between minimum and maximum. That is how we speed up and slow down motors, and it's done like that in industry as well. It's not just for model railways or model cars or boats or whatever it is we got, because we do need this torque, and that's just a law of physics. That's the way it is. Okay, now we're talking 12 volts, but it might not be 12. You might have a 6 volt motor, or you might have a 24 volt motor. I mean, you could have anything, couldn't you? But as long as it's DC, this is how you do it, right? We're not talking about AC here. So we're delivering a train of pulses many hundreds or thousands of times a second, and all we're doing is changing the width of that pulse, and then, well, by changing the width of that, you're then changing the width of the space in between, and that determines the speed. So this is called the space, and this bit here is called the mark. mark space ratio, and that determines the speed. And as I said, because we've got 255 levels to play with the Arduino, we could say the mark space ratio is 1 to 254, so 1 on and then 254 periods of not being on, which would be extremely slow. Or we could do it the other way around and say 254 on to 1 off, which is effectively full speed. So that's the mark space ratio. Okay, that's probably as much as you need to know. You can watch my other videos, as I say, to find out a bit more about pulse width modulation and how we can use this to not only turn motors, but you can use this to turn on bulbs or LEDs. In fact, the dimmer in your home, I know it's AC, it works slightly differently, but it is a sort of a pulse width modulation, sort of, but I'm not going to go into that because that's AC and it chops the wave up a little bit differently. But anyway, for DC purposes, this is how we control either the brightness of a DC light or the speed of a rotating motor. Okay, the difference between the mark and the space, from full on to full off, and the 255 levels in between. Enough, let's move on. So much for the theory then, and it's pretty straightforward and simple, isn't it? Really, just delivering a train of pulses. But the magic here is, I mean, I've turned off the main LED now. It's getting a little bit annoying even for me, but I have left the LED in, and you can see that's flashing away quite happily. The slight odd effect you're getting is that occasionally the camera misses a flash. I don't know if you can just see that. It flashes and then there's a little tiny pause sometimes. A bit odd. Ignore that. Just take it from me, it's working properly, okay? Right, now the thing is, this is flashing at about, I don't know, what, 2, maybe 3 flashes a second, if that. But the Arduino can't do that, not out of the box. In fact, if we look at the browser window here, what you can see here is that on the 3 timers, because the Arduino does have 3, timer 0, by the way, which is on pins 5 and 6, you don't really ever want to play about with timer 0. Timer 0 affects things like your millis command, which well, grabs the number of milliseconds since the program started running, since the Arduino was booted up effectively, and it's used extensively in determining how much time has passed in various programs. We've used it in this series of videos extensively. And also it affects the delay command. So if you put in delay 1000, you'd expect it to delay for 1 second or 1000 milliseconds, not 1200 or 800 or something. So timer 0, we wouldn't normally want to play about with, but it has got two more timers. Timer 1, which is on pins 9 and 10, and timer 2 on pins 11 and 3. Now the 2 pins that we've mentioned here on both these, whether it's 9 and 10 or 11 and 3, the frequency on those pins is usually the same for each timer. I think it might have to be, not sure, but it's usually the same. But you can have different mark space ratios. But that's not what this video is about. Let's concentrate on one of these timers. We're going to concentrate on timer 1 because it's a safe timer. They're on pins 9 and 10, nice and close to each other. So we can play about with that. Now look, if you see this here, look. By default, the frequency is 490 Hertz. Now you might think, well, 490, does it matter? Well, yeah, it does really. If you look at my previous videos, you'll notice that 490, whilst it will work on a motor, something like a fan, I think I used a computer fan and a small DC motor as well, it works, but it can be noisy. You will hear 490 Hertz. I mean, 490 Hertz is sort of a high-pitched hum, isn't it? Not quite a whistle, but it is a hum. So, you know, sort of a and that's exactly what you'll hear on the motor or whatever as it's trying to turn around, especially if you've got the mark space ratio set down low, so it's a very slow speed, you'll hear that more and more. In fact, in your house, if you've got dimmer switches, you may hear a buzzing from those dimmer switches because the mains frequency is at 50 Hertz or 60 Hertz, depending on where you live in the world, and they will buzz. Well, we don't want the Arduino motors to buzz, and 490 is a bad frequency to use for motor control. It's fine if you've got a model car or a boat or plane or whatever it is you're trying to control. You don't really care about the noise then. But in the example in those previous videos I mentioned, I have an extractor fan in my computer cupboard to keep it cool. and I could most certainly very much hear the frequency that I was using. Now at the time I wasn't using an Arduino. Shock horror. Yes, I used to use microchip stuff, but even then I could hear the buzzing. I think I chose something like 1,000 hertz at the time, and it was very audible, unpleasantly so. So I had to change the frequency. Now normally you can't change the frequency of Arduino, although you can if you watch my previous videos. It's all a bit convoluted really. You have to use commands like this. I mean, it's simple enough, but even then we only get these fixed frequency. You can have 31 kilohertz, that is, which is good for a fan motor or something like that. You won't hear that. 3,900, you will hear that. 490, as I say, and then of course it's just getting slower and slower. But you still can't get what I've got down here, which is about 1 or 2. In fact, the slowest I can do on this one, I think it's about, yes, it is 1. It is 1 flash per second, and then it goes off. In fact, I can make that a little tiny bit brighter by adjusting something else here. There we are. Now you can see it flashing quite well, I think. Yep, 1 hertz. That's on, off, on, off. How do we do it? Well, there's another library available now. Let me just show you where that is. That's on here. Now, the Arduino PWM frequency library, there's well up to library version 5 now, but that's been around since September 2012. So that's quite mature, and I guess the fact it hasn't been updated since probably means it's as good as it's going to get. But what that does mean code-wise is that it is extremely simple to set the frequency on an Arduino now. Let me bring up the code window and show you. Now this is the simplest bit of code you could ever want to get. We've installed the library, the one I just showed you, version 5. So there's the library at the top, that one there. We're using PWM pin 9. As I said, you want to avoid timer 0. So pins 9 and 10 are a good bet. In the setup, init cipher safe, that's from the library. Now the safe bit means we're not touching timer 0, which is exactly what we want. If you want to play fast and loose and cause the end of the world to come, then you can always use init timers, and that will also affect timer 0. So if you're not using millis or delay in your program, it's probably as safe to use as this one here. And then we're going to say set pin frequency, once again safe, but if you don't want the safe one, you don't need to put that safe bit on. However, in this one we're using it in both. So here's our PWM pin, which pin 9. Now I'm saying set the frequency to 100. You can set it to absolutely anything you want here, down from, I don't know, 1 to, well, 30,000 I suppose, 40,000. I don't know what the Arduino could go up to. I think it can probably go up to beyond 65,000. In fact, there's no reason why it shouldn't go up to several megahertz really, if it's doing nothing else. I don't know what the limit is for a PWM. Perhaps we'll try it and put it on the scope in the workshop in a minute and just see what it can go up to. I've just chosen 100 here because down here on the bench here, we've got this little LED just to prove it works. And if I twiddle this little pot, these are good, these little pots. Look, you can buy these. Let me bring the workbench back into full view. These little pots are good for when you're mucking about on the workbench. I mean, I wouldn't use them in a finished product, I don't think. No, not really, because pots are easy to mount on the front panel anyway. But for mucking about on a workbench like these are great because they come with this lead here, and you can just plug them in there at the other end. I mean, they're great. So by twisting this, you can see it goes brighter and dimmer. In fact, between 0 and, well, 255, and that's pretty bright. You can see it causing a bit of glare on the camera lens, in fact. Now, right at the extreme end, when I get down to sort of the 1, I guess it must be about 1, as I'm just turning this extremely slowly clockwise, just to get enough coming out so we can see it. There it is. Just enough. I do there. I know you can get it. You can see a little bit of flicker. Now, I'm pretty sure it's not this, but we can test that downstairs in the workshop as well. I think it's the LED just perhaps not responding as we might expect it to, because 1255 of a second, having a little blip on there, it's not a lot really, is it? As soon as you go above another number, that's nice and smooth and really works well. So back to the code window then, just look at the last couple of lines. So what I'm saying is go and get that value from A0. So this pot is in fact connected to A0. Ignore the fact I've had to put unsigned char in there. I mean, yes, it's true, it is an unsigned char, but this particular IDE I'm using doesn't want to recognize A0 as an integer. Now I could have put pin 14 in there because that's what A0 is. You could use 14 as well. 14, A1 would be 15, A2 would be 16, and so on. You can use that quite happily. These are only aliases, these A0s, for people who use the Arduino IDE. So what we're doing is an analog read then on A0 from this pot, which is connected to 5 volts one end, 0 the other, and we're taking the output, just like the circuit diagram that we had here. So it's just one of these, okay, A0 plus 5 volts, there's the resistor down to ground. So we're taking something between 0 and 5 volts in. Now the A0, or all the analog inputs on here, have got a 10-bit resolution. It means then you get between 1024 individual steps, 0, 1023 being the min and max. Now we're taking that value and we're saying, well, now we've got to map that between 0 and 255 because that's what the pulse width modulation pin would expect, a value between that. But instead of, we could divide by 4 in this occasion. We can say, right, I've got 1023, divide by 4, that'll give us the output, but why bother? Use this map. I use it all the time in quite a few of my bits of code. I'll go, right, I've got some kind of input range. Doesn't matter what it is, you know, as long as you know what it is, of course, as a developer. You go, great, I've got something between 50 and 1,000, but I need to map that down to something I can manage between 10 and 50. Well, that's what map does. It just does all the calculations behind the scene for you. It's brilliant. So this is how you might use it in your code here. So we're saying take the input value from our little potentiometer, which could be anything between 0 and 1023. And we're telling it that in fact that is what it can be input as, somewhere between that. And then we're saying I want the output to be mapped between 0 and 255. So it does. So then we output on PWM pin 9 whatever the mark space ratio of this. So we're not changing the frequency, remember, we're changing the mark space ratio. How long, if you like, the on period is for any one of those pulses. Now the frequency we've got this at now is 100, so there's 100 pulses a second coming out, which isn't a lot. It's twice what we have in our mains frequency here in the UK. But for each one of those pulses, the amount of time that any one of those pulses is on is between, well, nothing, which is right down, to permanently on. But if we set it somewhere in the middle, somewhere like that, so if I zoom in on that LED a little bit so we can see it a lot clearer. So something like that. So it's somewhere in the middle, isn't it? It's off, that's full brightness, somewhere about there, be about halfway. So it's on for half the time, off for half the time. So 50th of a second on, 50th of a second off, which makes up the 100 hertz. What else? Oh yes, I've just put a little delay down here. Now what would happen if we put a delay of, I don't know, 5 seconds here before it read this potentiometer value again? Would the LED go off? No. And that's an extremely important point, and the whole point really about PWM pins on not just this microcontroller, but any one. Each microcontroller that has a PWM output, it's separate from the main microcontroller's CPU, if you like. It's set off, starts running, and will continue to run regardless of what else happens on that microcontroller. It's a separate piece of circuitry controlled by or initiated by the microcontroller, but once you've started it off, it will continue to run like that. So if you imagine you have a model car and you've set the speed to say a quarter speed ahead, go, the car starts running at that, and you can do anything else on that microcontroller, looking for obstacles, detecting lights, whatever you like, doesn't matter. It will not affect that PWM output. That's the beauty of it. And of course, the Arduino has got, well, if you take all the outputs we got 6 pins, but effectively 3 outputs. Some of the other microcontrollers, the Mega for example, has got more. Don't know how many off the top of my head actually, probably a couple more I think. It's got more timers as well to play about with. And other microcontrollers like the microchip has several timers and PWM pins. But the beauty of it is you set them off, they'll continue regardless. Fantastic. Right, I think I'm going to put this on the scope actually downstairs just so we can see the effect of the pulse width modulation in real time, and you can probably get a better picture of what I'm talking about. Let's go and do that now. So here we have it with the variable resistor set sort of mainly in the mid position there, and that's about right. You can see that it does say frequency 100 Hertz down below in the bottom left hand corner there, which is what we set it to. So now if I turn this resistor anti-clockwise, you can see that the pulse is getting thinner and shorter until eventually it gets all the way down to nothing. So that's totally off. And if I turn it the other way again, nice and slowly, so it starts off and gets wider and fatter. So if our motor was connected to this, it'd be getting faster and faster, it's getting more little pulses until eventually, if I turn it up enough, it's permanently on. It'd work exactly the same if we had 30,000 or 60,000. I wonder what the maximum is. Let's try that out next, shall we? Right, I've gone and changed the code just to change the frequency and nothing else, and as we can see there now, it says 1.000 megahertz. Now that is damn accurate, isn't it? Because that's what I set it to. I didn't know if it could do a megahertz or not. So let's change the mark space ratio now. So bring it up a bit. A little bit of instability there. I think that's probably my scope more than anything else. Let me right, so I've readjusted the scope and it's a bit more stable now. So it's 1 megahertz still, and I can bring down the mark space ratio, even though it is adjusting the position a little bit. I don't quite know what you'd use a megahertz for, but well, it's nice to know that we can do it. Certainly a lot different to the 490 hertz, isn't it? That's default. So very, very flexible unit indeed. There we are. Excellent. Oh no, we've run out of time already. Well, never mind. Part 2 is going to be issued pretty quickly actually, because I know how frustrating it can be to get part way through a video. I'm waiting for that next part. So that's going to be released imminently, and it deals with the circuitry you see on the workbench as we see it here. So stay tuned and wait for the next part. Thanks very much for watching. See you in the next video. I hope you're finding these videos useful and interesting. Please leave comments down below, subscribe, share and give me a thumbs up. Thanks for watching. See you in the next video.